yeah, thank you so much. First of all, I wanted to say thank you so much for having me here. It's a pleasure. I'm super elated to have this opportunity. And yeah, so today I'm gonna speak about the bus driver scheduling problem. So whenever you want to interrupt me, please do it. And this is a joint work, yeah, with Nusser Buslio, my supervisor, Lucas Alexander at the TU Wien in Austria, and Kate Smith-Miles. So during my presentation, I'm going to speak about first of all, the problem, what this problem is about, and what are the constraints that we have. Then, what are the algorithms of the state of the art, and the main core of my research, they will be about instance space analysis. So, what are the features and what are the characteristics of the instances that we can study. So, the bus driver scheduling problem, as you can imagine, is a scheduling problem. And we can think of it like as a subset of the transportation planning system. So we deal with crew scheduling, in particular with bus drivers scheduling. So we already have the timetabling of vehicles, we already have the scheduling of vehicles, the routes are already predetermined. Okay, so we have every start time, end time, start position, end position of every vehicle in the city. What we want to do, we want to schedule the crew. So in particular, we want to assign, we have a set of bus vehicles, and a set of employees, of drivers, and we want to assign every vehicle to a driver. This is an optimization problem, so we want to do it in an efficient way. And yeah, okay, in an efficient way, and of course we want to respect the laws, the collective agreements. And we have essentially two goals. On one hand, the bus driver company wants to save money and wants to minimize the costs. On the other hand, the employees want a better working environment. So we want to maximize the satisfaction of the employees. So here we have an example of a bus tour. So a bus, you can see three nodes. Each of these nodes is a bus stop. In reality, actually, 0 is the bus depot. So if you think about it, what does a vehicle do during the day? A vehicle starts from the depot, from 0, then it travels from the depot to a bus stop 1, and the driver takes a break. Then from bus stop 1, you can think about it as an end of lines, the ends of a bus line. From bus stop 1, it goes to bus stop 2, takes a break, and then from bus stop 2 it goes back to bus stop 1, and so on and so forth, until when, at the end of the day, it goes back to the depot. This is what we call a bus tour. And every vehicle is associated to a bus tour. And each of these arc is what we call a bus leg. In the literature, you can find other words like spell or pieces of work. Here I place a table. So each leg has an associated tour, a start time, an end time, a start position, and end position. Okay, so this is an example of a bus tour with 4 bus legs. 1, 2, 3, 4. But in the reality, the things are more complicated. This is one of the largest examples we have. So we have 10 positions, and as you can see, there are many bus legs in this graph. So 0 represents the depot. I don't know, am I allowed to ask the audience a question? Okay, so this was interesting. I discovered it recently. So if you look at here, at the position 0, so at the depot, there is a vehicle there is a loop, a self loop. So there is a vehicle that is starting from position 0 from the depot. It travels a bit, and then it goes back to the depot. Can you imagine a situation in real life in which there is a vehicle that does like this? Refill. Or?
Maybe they're taking a break and the bus actually in the depot all the time.
Okay, interesting.
Well,
So,
am I right in saying that a node is not a bus stop, it's a place where it's safe for the driver to change? And so this is a route where they go somewhere, stop, but it's not safe for any of those places to change until they get...
yeah, exactly. So right point. So I should point it out. So these are not all the possible bus stops in a city. These are all only, let's say, bus stops in which there is a possible changeover. Because in the majority of the bus stops, you don't have any decisions. We don't have decisions to take. They just passes through a bus stops and just leaves. Instead, these are points in which can, let's say, change over, or can take a break, or change vehicles. So yeah, thank you. So yeah, the easiest way is like a school bus. So a school bus, they start from the depot, they travel around the city, they bring the kids and they leave them at the school, and then they go to the depot. They usually don't have changeover. Okay, whatever. Okay, so this was so this is a representation, let's say, a background representation throughout all the day, but this doesn't take into account the time. Okay, so this is what we see in an entire day. Yeah, we are designing shift to one day shift, daily schedule of bus drivers. There is another representation that deals with time. So if we forget about the space, let's say the geometry, and we only deal with time, we have this representation. So on the x-axis there is the time, spanning from 6 a.m. to midnight, more or less. And every row is a bus tour. And every row, as you can see, is a sequence of several intervals, several rectangles. Each of these rectangles was an arrow, an arc on the previous graph. So here we have 1, 2, 3, 4, 5 bus tours, 5 vehicles. So this is not a solution, this is just the instance input that we have. What is a solution? Then a solution is this. So mathematically a solution is a partition of bus legs. And every block of this partition in real life is an employee. So for example, if you look at the 3 purple legs, there is an employee that is driving, I don't know if you can see the number, but bus legs 19, 20, 21. And then the driver goes back home. This is a shift of the driver. And this is what a solution looks like. Yeah. So regarding the constraints, there are many bus driver scheduling problems in the world. This problem really depends on the region. There are regions in which there are some constraints. In other regions, the constraints change a lot. So right now, I'm telling you something about the bus driver scheduling problem with Austrian regulations. So with regulations that come from the collective agreements of Austria, that is very specific about breaks. So over the next few slides, I'm gonna say to you something about the regulations, the constraints of the breaks. So for each employee, each bus driver can drive at most 9 hours, at most. But they can drive at most 4 hours consecutively. What does it mean? It means that after 4 hours of driving, they have to take a break. So this break can be either a break of 30 minutes, or 2 breaks of 20 minutes, or 3 breaks of 15 minutes. And okay, this is not the end of the story, because after one driver has completed the breaks they need, the driving block of 4 hours starts again, it resets. What does it mean? It means that if you do 1 hour of driving, maybe I should say it here. If you do 1 hour of driving and then you complete your breaks, you can drive 4 hours again. So an implication of this is that we have to store, for each bus driver, we have to store the amount of driving breaks that every employee has had. And if we perform a move, so we say, for example, we swap, an employee doesn't drive this vehicle anymore, drives another vehicle, and maybe we swap 2 different vehicles, we have to reevaluate everything from scratch, because maybe the driving brakes are messed up. And again, this is not the end of the story, because if you think about it, a bus driver can take a break from driving. For example, they can act as a passenger. They can get on a bus, act as a passenger, go from one bus stop to another one. This is a driving break, but this is not a break in which they can rest. This is not a break in which they can, I don't know, smoke a cigarette or having lunch. That's why we need another type of break, that is a rest break. So, yeah, I don't want to give you too many details, but what I want to convey is that this problem is really constrained is highly constrained, and I believe the major difficulty is about breaks. Because some rest breaks are, every rest break is driving break, but not all the driving breaks are rest breaks. And there are other constants. For example, some of the rest breaks are paid, some of them are unpaid, and where are they paid? When are they paid? It depends. It depends whether a break is between the first 2 and last 2 hours of the shift. So again, this implies 2 things. First of all, that you have to store the entire shift, and if you do a move, so for example, you remove the last vehicle, then you have to reevaluate everything from scratch, because the first 2 hours are different. Okay, so also evaluating this, what we call the delta evaluation. So when we do a move in a heuristic and we have to evaluate how much the objective function changes, then we have to take into account this. So it's tough to have a good delta evaluation. So evaluating the objective function is pretty consuming. And yeah. So regarding the objective function value, we have this sum. So it's a sum over all the employees, all the bus drivers, of 5 things. 3 of these things are things related to time. So we have the amount of time that is paid to each employee. Then we have the total time, so the span of the shift between the very beginning and the very end. Then we have the passive ride time, so the time that an employee is riding as a passenger. And these are the costs that the company wants to minimize. On the other hand, we have 2 other objectives. There is the number of bus changes for employee E, which is usually badly regarded by the employees. That's why we penalize them with 30 minutes. And then there is a split shift. That is a break that is larger than 3 hours, and which is also usually badly regarded by the employees. So yeah, we have this linear combination, and the combinators, so let's say the coefficient 2, 1, 130, 180 have been decided together with the bus driver companies. Okay, so this was the problem, more or less. And regarding the state of the art, this problem has been studied a lot. There are many algorithms for very different problems. In red, I wrote the algorithm that deals with the Austrian, let's say, Austrian collective agreement bus driver scheduling problem. So we have exact methods, so methods that if they end, they gives you the best. They give you the global optimum, the best possible solution. Then there are approximated method heuristics. So hill climbing, simulated annealing, taboo search, and iterated local search. And let's say until few months ago, branch and price was the state-of-the-art method for small instances. So it really performs very, very well for until, I don't know, 20 employees. And taboo search was the state-of-the-art for larger instances, so instances with hundreds of employees. But Roberto Maria Rosati, in November 2022, came up with an idea, an amazing idea according to me. So they hybridized some methods, exact methods and heuristics, and he came up with constraint merge, solve and adapt method. And yeah, here I have a table which is very bad, but we can see that we have instances, we have 65 instances grouped by size, and yeah, for instances up to size 90, so 90 bus tours, branch and price has the best objective function. Remember, we want to minimize, so the lower the better. And CMSA is so the method developed very recently outperforms taboo search for the largest instances. For the very larger instances, branch and price doesn't even stop, so we can't even use it. So at the moment, what we are trying to do with Vienna, at Vienna, we are trying to use branch and price that works very, very well for smaller instances in as a repair method of ALNS. So yeah, I can show you. I'm sorry for people at home, but essentially, so we have a problem that we can't solve. This problem is too large to solve. So what we do, we destroy this problem in a sub-problem. So we consider this a problem, and with branch and price, so with an exact method, with a repair operator, we exactly solve these problems. And then what we do, we reinsert this problem in the original problem again. And we start again. So we destroy another part of the problem, and we iterate this procedure. And so far it's very promising. And I don't have clear results so far, but so let's say my few experimentations are showing that it's very good for very large instances. And yeah, so this is what we see so far. So with the current 65 instances. But I'm here also to explore what are the instances, what are the characteristics of the instances, and how can we generate more instances, more diverse. So I have to say something about the instances. So we have, as we said, 65. 9 of them we can optimally solve in 1 hour, and the other 56 we can't. Each of these instances has 10 bus stops, and we have a distance matrix that so how long, what's the time that we need to drive to connect to different bus stops. In general, this is not always the Euclidean distance, because if there is like a hill or a lake in between, we can't use the Euclidean distance. So there is a perturbation term to make instance more real life based. For each instance, we have a set of bus tours and a set of bus legs. Bus tours span between 8 and 250 bus tours for the very large instances. So this is what we have right now. What we can, let's say, something that we can explore is the demand of the distribution. So as you can see, this is a demand of one of the largest distribution that we have. On the x-axis, there is the time. On the y-axis, there is the number of active vehicles. So there are two peaks in this graph, in this plot. One peak is for people who go to work or go to the university or go to school in the morning around 7 a.m. As you can see, there is this peak, and after this peak, some of the vehicles go back to the depot, but not all of them. Some of them stay active until when there is another peak, people who may want to go back home after having worked or after the university. And so we need more vehicles, and then it lowers down. Okay. So this is what we have. This is our distribution demands of our instances, which is interesting, but maybe we can play with this. So we developed an instance generator that's actually modified this. So, sorry. Okay, I can show you. So this was the image before, so with 2 peaks, and this is an image that we have generated with a new instance, that we have generated. So in this case, there are 1, 2, 3, 4, actually 5 peaks. So we added some peaks in the afternoon and the night. I don't know, maybe it's Friday night and people want to go party, and you need another peak during the night. So this is a parameter that we can play with. And for the instance generator, we have many parameters. There are this number of peaks of the demand. So we can play with the number, the height of each peaks, and also the number of bus stops that we deal with. And it's very promising, and we hope to generate more diverse instances. And each instance has some features that we have to explore. Some of the features are like characteristic of the problem. They should tell us how diverse 2 different instances are, or how difficult can an instance be, according to some algorithms that we have. So some of the features are very, I would say, straightforward, like the number of bus legs and the number of bus doors that we have. Some statistics about the length of brakes and legs. And some features are based on the space, like how many bus stops and what is the average distance between bus stops. But it's clear that there is more. It was clear that we can come up with some new features, some new feature. So if we go back to this very plot that we showed at the beginning, to this graph, I told you that this is not a real instance, what a real instance looks like, because this is just what happens throughout the day. And what we can, I have an animation, so I hope I can, So what we can see, so I created this animation with, wow, you can see, just a second. You can't see anything. So I should stop share here, share screen, and this. Okay, can you, I hope you can see it. So as the title says, there is an interval, a time window between, in this case, 3 a.m. and 3 and 4 a.m. So 1 hour of time window. And we can slide this time window and see how the plot changes throughout the day. And as you can see, there are time windows in which the demand is higher. So remember, every arc is a bus, is a vehicle that rides between two different bus stops. Okay, so this is what we can see. And I believe it starts again. Okay, so yeah, so this is what we observed. And so our idea was, okay, why don't we focus on, let's say, one position, let's say one bus stop, for example, bus stop 7, and we have a look at what happens throughout the day at bus stop 7. So for example, here, there are many bus legs that start and arrives at bus stop 7. It means that we have many possibilities to change, many decisions that we have to take, that we can take. So let me share the screen again, the other one. Share screen. Okay. Also, yeah. Okay, so yeah, this is why we came up with our term relief opportunity. So we fix a bus stop, we fix a position, a node, and a time window. In this time window, in this node, a driver can take some decision, can take a break. Sorry, we can take some decision for the driver. The driver can take a break or can switch to a different vehicles. And this for us is a relief opportunity. And our idea is that if there is an instance with many relief opportunities, then this instance it's easier to improve the solution. It's easier to come up with a better objective function. This is similar to what happens in local search. If you have many possible moves, then maybe it's easier to find ways to improve the objective function value. And yeah, this is what we are doing right now. So we are trying to we are studying for each positions. We are studying what happens throughout the day. So here we have let's say we have a span of time between the very beginning and the very end of the shift, and we can divide the time into equidistant intervals, tau 0, tau 1, and so on and so forth. And for each of this interval, we can evaluate what happens over the next, let's say, 1 hour. So we fix a position, a bus stop, and we fix a time window size. And what happens that we count the number of legs that passes throughout the bus stop, through the bus stops between time t tau plus h. Now, I just realized that I made a mistake because I called two different things with the same name. So this H should be some other. Please think about this H not at the same H here. So the idea is that this H can be very small. Maybe we divide the entire day into multiple, let's say, minutes. So every minute we evaluate position how many relief opportunities there are for every minute. Instead, this H is like 1 hour. So we are, I don't know, 10 a.m. and we evaluate what happens at position, let's say 1, for the next 1 hour. 10 a.m., 1 minute, we evaluate the next 1 hour, and so on and so forth. So we have this time windows that is sliding throughout the day. Let's say we can evaluate it every minute. So this we did it, and we are still trying to understand something, but this is the initial plot that we have. So at the top there are okay. So there are 4 plots, but only 2 positions are shown. At the top there is position 7, and at the bottom there is position 8, or for the very same instance. On the left there is a time window of 60 minutes. So again, every minute we evaluate what happens over the next 60 minutes, and on the right, every minute we evaluate what happens over the next 2 hours, 120 minutes. Okay, and as you can see, the graph is similar. The plot is, I would say, pretty similar. Same thing here. So the plot at position 8 is a bit diverse, in my opinion, to the plot at position 7. But it's similar to the plot at position 8 if we double up the time window size. Okay, so what's the point? The point is that we believe that it might be interesting to study the plot, so to study the shape of each of these time series. So yeah, are these 2 time series different? Like, are they shaped different, or aren't they? I'm here because I still don't know. So I'm really, I know nothing whatsoever about time series. So if anybody knows anything, feel free to chat with me later. So yeah, we believe that we can maybe try to cluster for each instance how many different shapes we have for each positions. And to analyze this cluster, to analyze these different shapes of the same instance, of different shapes of this time series, of relief opportunity series. And maybe this can tell us anything about the difficulty of an instance. And yeah, so this is the question that we are studying, let's say. How can we characterize the instance by each time series? So what kind of information do these time series provide? And can we cluster different shapes of time series within the same instance? And what can this tell us? What can this tell us? Yeah. So, yeah. Because this is the last slide regarding the conclusion. Sorry. Regarding the conclusions, I show you that the Bachelor scheduling problem is a difficult problem. Actually, it's NP-hard. Has been shown to be NP-hard, and there are lots of constraints. There are many algorithms, but there is no clear winner so far. And we have some real-life based instances, but we also have a generator that we can generate other instances, more diverse and more maybe difficult to solve, and with different characteristics. And yeah, this is what I'd like to do in the future. So I'd like to study what happens to these relief opportunities with this time series, and I would like to generate new and diverse instances that maybe they take into account these things. Maybe we can generate diverse instances also with diverse time series shapes, relief opportunity shapes. And when we have this, and when we have also the new algorithms that I let's say presented to you, we'd like to perform an instance-based analysis. And so yeah, this is the end of my talk. I hope I opened time.